Hello everyone, I am Tetsuya Kawanishi from Waseda University, Japan. In this presentation, I'd like to talk about basics and recent progress in Lightwave modulators. Here, I'd like to explain the concept and the configurations of the Lightwave modulation schemes and devices. This is the outline of my presentation today. First, I'd like to talk about roles of optical modulation in photonic networks. As you may know, the optical modulators would have important roles in high-speed optical fiber communication systems. These devices would be also useful in the various types of applications, such as the high-performance sensors. In the second part, I'd like to talk about the concept of direct modulation and external modulation. There are various types of modulation devices, but they can be divided into two, the direct modulation and the external modulation. In this presentation, I will focus on modulators based on electro-optic effect. Electro-optic effect offers refractive index change of the material proportional to induced the electric field. So by using this effect, we can configure optical modulators. So here, I'd like to talk about the optical phase modulator first. The electro-optic effect-based modulators can offer precise and high-speed light wave modulation. That's why I focus on the electro-optic effect modulators here. And then I will talk about Mach-Zehnder modulators. Mach-Zehnder modulators have Mach-Zehnder interferometers on the integrated circuit. By using the optical wave interference, we can convert phase modulation into amplitude modulation in the integrated circuit. Such modulators are commonly used in various types of transmission systems. In the last part, I will show you some examples of advanced modulation technologies which offers precise optical modulation. Here I listed two references. The first one is on optical modulation. The title is Electro-Optic Modulation for Photonic Networks. If you are interested in the details of the electro-optic modulation, you can find more detailed information here. And the second one is on wired and wireless seamless access system for public infrastructure. This book is on various optical systems which can be used in public infrastructure, such as railway system, airport, and power grid, and so on. But in this book, I wrote two sections related to optical modulation. Section 5.3 is on the basic concept of optical transmission system. You can find useful information to understand optical modulation. Section 10.3 is on Mach-Zehnder modulator itself. So if you want to find a concise the explanation or chapter on the Mach-Zehnder modulator, it's a good idea to check this section. Okay, here I'd like to move on to the first section of this presentation, the role of optical modulation in photonic networks. This slide shows the basic configuration of digital transmission systems. As you may know, almost all types of data are described by electric signals and processed by the electric circuit. But for long-distance transmission, we often use optical fibers because optical fibers can offer low-loss signal transmission. So we have to use optical transmitters, which can convert the electric signals into optical signals. We call that function the electric to optical conversion, EO conversion. On the other hand, in the optical receivers, we need the OE conversion devices. Of course, in this presentation, we will focus on EO conversion realized by the optical modulation. This is the radio over fiber system, which can offer the transmission of waveforms or radio services. Now we rely on the radio wave communication services. For example, the mobile communication services with smartphones. To offer high performance radio services, we have to install many remote antenna units and base stations. In order to offer such the services, we have to configure the high performance optical networks which connect the remote antenna unit and the base stations effectively. One of the required functions in such networks is the waveform transfer over the fiber. Here is a radio signal, and here is the electro-optic conversion devices. We can modulate the optical signal by the RF signal waveform, and we can take out the RF signal waveform at the remote antenna unit or base station by using the photodetector. Photodetector acts as an OE conversion device. So, to achieve the high performance waveform transfer, we have to develop the high speed and the high performance the optical modulation devices. In other words, we have to have the high speed and precise light wave control by the electric signal. This slide shows the basic function of radio over fiber, in short ROF. As I mentioned in the previous slide, the waveform can be transported over the fiber by using the EO and OE conversions. By using radio over fiber, we can simplify the configuration in the OE and EO conversion system. If we cannot use the waveform transfer over the fiber, we have to have complicated signal processing function at the border of the transmission media, I mean the electric signal and the optical signal. But if we can configure transparent the waveform transfer, we can place the required signal processing function anywhere you want. This is the most important function of radio over fiber. Here is an analogy by the transportation of the truck cars by the ferry ship. The purpose of ferry ship transportation is to transfer the parcel or some cargo on the truck cars. But by using the ferry ship, we can simplify the process in the marine port. If we have to take out all the item on the trucks, and we have to put them on the ship, we have to have the complicated management function or the parcel, the processing function at the manifold. But by using the phase shift configuration, we can simplify the process at the manifold, and we can place the parcel management or cargo management function anywhere you want. So the transparent transport or signal transmission would offer the effective system configuration. This is a very important point of the important function of radio over fiber. Okay, here I'd like to explain the basic configuration of optical modulation. Here is an electric signal, and here is an optical signal. The optical modulator can generate the optical signal based on electric signal. In other words, the optical modulator would control the amplitude, phase, or frequency of light wave by electric signal. This is the basic function of optical modulation. Okay, in this slide, I'd like to offer you some simple mathematical expression to describe the basic configuration of optical modulation. Here is an optical input, a modulated signal, which can be described by the sinusoidal wave, as you can see here. Here is an electric input, modulating signal, denoted by Ft. And this is the modulated signal, optical output. Amplitude, frequency, or other phase would be modulated by the electric signal Ft. Okay, here I'd like to explain the simple modulation scheme, amplitude modulation. As I mentioned, the optical output had three components: amplitude, frequency, phase. But in the amplitude modulation, we consider only this part. So this part would be described by this simple equation. So no frequency change, no phase shift. Here we focus on only this part. And we consider the very simple amplitude modulation. Amplitude modulation by a single-tone sinusoidal signal, which can be described by this term, cosine omega mt is a modulating signal. By using a product to sum trigonometric formula here, we can get such expression from this one. It has three terms. The cosine omega 0t, the frequency is same as the optical input. And here it's an upper sideband whose frequency is higher than this one. Here is a lower sideband. The frequency is smaller than this one. So through amplitude modulation, we have three spectral components. The first one, we call it the carrier component. The frequency is same as the input of optical input, but we get the frequency shifted component, upper sideband and lower sideband. As I mentioned, through the amplitude modulation, we can generate upper sideband and lower sideband. But we have to use the more complex, the mathematical expression. Actually, the sideband component intensity should be described by Bezel functions. If we want to check the details, please refer this book, as I mentioned. In the Bezel functions expression, we have many sideband components like this. If the modulation signal intensity is very large, we have a number of sideband components. But if the modulation signal is small enough, we can neglect the higher order sideband component. Here is a carrier component. We call them first order sideband component. There are second order sideband components. By using the Bezel Functions expression, we can get the formula to describe higher order sideband component. But in a small signal modulation, we can neglect the higher order sideband component. If we just focus on the first order sideband component, we can use the simple mathematical expression which I explained in the previous slide. Here I'd like to talk about amplitude modulation by multispectral components. In telecommunications system, the waveform would be complicated. I mean, it has many frequency components. So here we use the mathematical expression like this to describe such the signal. It has many spectral components. In that case, we have many upper sideband components and lower sideband components. So we have wide spectrum of the amplitude modulation signal. In general, the waveform should be described by the continuous the spectrum. The sideband spectrum would have continuous distribution. So the modulated signal would have spectrum like this. It has the distributed spectrum, and we can define the bandwidth of the signal. In other words, the signal with the information would have some finite bandwidth, as you can see here. If we look at the modulated signal in the time domain profile, we can get a complicated waveform like this. But it's not easy to get the useful information from the time domain profile because the waveform is very complicated. So we often use the frequency domain spectrum to understand the modulated signal. Okay, here I'd like to talk about the frequency component and the phase component. Here we define instantaneous phase by this equation. By using instantaneous phase, the modulated signal can be described by the amplitude part and the phase part. The instantaneous phase includes the frequency shift from the original frequency and the phase shift. The frequency excursion from the carrier frequency can be expressed by the this equation, the derivative of the instantaneous phase. And from this equation, we can get such equation by using trigonometric formulas, as we did it in the simple amplitude modulation. So the modulation can be described by the combination of the amplitude modulation for cosine function and sine function. We call the modulation on phase and the frequency angle modulation because it's associated to the angle part of the sinusoidal wave. As I described in the previous slide, it can be described by the combination of the amplitude modulation for cosine part and the sine part. So the spectrum shape is same as in the amplitude modulation. So in other words, in the angle modulation, we also get the finite bandwidth signal through the frequency modulation or phase modulation. Okay, here I'd like to explain the modulation speed and data rate. There are various types of modulation scheme. They can be divided into two types. The first one is binary modulation. It has only two symbols. So we can send 0 or 1 by now one modulation step. Another one is multi-level modulation. We can send more than 2 or more bit in each modulation step. For example, in that case, by using the 4 level, we can send 2 bit per one modulation step. The modulation speed is described by baud rate. Baud rate is defined by this equation. Tp denotes the period of the pulse or the period of the modulation. So the FB describes the modulation steps per second. And bit rate that denotes the transmission speed, it would be given by this equation. Here is the number of symbols. If the number of symbols is 4, we can transmit the 2 bit per one modulation step. So by using this equation, we can describe the total bit rate. And this bird describes the how many bit we can transfer per single modulation step, and this bird describes how many modulation steps we can offer per 1 second. So this equation describes the total bit rate. Of course, if we can increase the number of symbols, we can easily increase the bit rate, but it's not easy to generate multi-level modulation signals. We have to use a complicated modulation scheme, and we have to take care about the noise because the difference between, for example, these two symbols is not so big if we compare with binary modulation scheme. So if we have some undesired noise, the binary modulation format would be robust, more robust. But the multi-level modulation the scheme, we would have the large impact from the noise. Okay, here I'd like to explain the bandwidth of the signal. So as I mentioned, the modulated signal has some finite bandwidth, and the bandwidth is dominated by the highest frequency component in the signal. Here we consider the simple binary modulation format. In such the binary modulation format, the highest frequency component would be associated with 010101. Here you can see the pulse shape 010101. Obviously, it has the frequency component described by the dash sinusoidal wave. So the TP is the modulation period, and the period of the sinusoidal wave is Tk. So the Tk is a double Tp. So the frequency of the dash component would be equal to the half of Fp. Fp is the baud rate. So the half the baud rate is equal to the highest frequency component. And here, the bandwidth of the modulated signal would be described by this equation, bandwidth of the modulation signal, because it has the upper sideband and the lower sideband. So there is a factor of 2. So finally, we can get this equation. The bandwidth is equal to double the highest frequency, but Fk is the half of the Fp. That means the bandwidth is equal to Fp, modulating the speed baud rate. And this is a very simple expression on the bandwidth of the signal. Here I'd like to explain multiplexing and the demultiplexing techniques. As I mentioned, by using optical modulators, we can generate optical signals for data transmission. But the transmission speed will be limited by the bandwidth of the electric signal and the modulation speed of the device, which device can handle. So to increase the total transmission capacity, we often use a multiplexing technique. We use many transmitters, as you can see, and we can combine the signal together with some special devices. In the receiver side, we use the demultiplexing device, and we can use many receivers, and we can get the electric signal in the many channels. You can find more detailed information in section 3 in a wired and wireless seamless access system for public infrastructure. The most popular multiplexing technique is wavelength domain multiplexing, WDM. We use the many optical transmitters with different optical frequencies, in other words, wavelengths. And we can combine many optical signals with different wavelengths. This shows the spectrum of the wavelength domain multiplexing WDM signals. Here's the channel 1, for example, channel 2, channel 3, channel 4. And by using the multiplexer, we can take out, for example, channel 1 here, and we can feed this signal to the receiver. So we can transmit, for example, channel 1 signal here from here, and we can detect the signal by receiver here. And these two, the pair of the transmitters are for channel 3. By using this scheme, we can increase the number of channels. And the wavelengths close to 50 nanometers are commonly used for high capacity transmission. It is called C-band WDM channels, conventional channels. But now we can use various types of the bands to increase the total the capacity. And the channel is defined by this equation. The n is an integer. It's 193.1 is a kind of the anchor frequency to define the WDM, the channels. Okay, here is an example of the multiplexing device. The name is AWG, Arrayed Waveguide. By using the interference between the optical signals, we can combine the, for example, the 4 WDM channel signal here. If we input the WDM combined signal from here, we can discriminate the WDM channel like this. So we can use this for multiplexing and also for demultiplexing. Here I'd like to move on to the next topics, direct and external modulation. This slide shows the basic configuration of direct modulation and that of external modulation. In the direct modulation, we control the electric current injected into the laser. So we can control the optical intensity from the laser. The configuration is very simple, but modulation speed is limited by the response of the laser itself, and it has a large chirp effect. I will explain the chirp effect later, but it means undesired phase shift or frequency shift. Even if we want to change the amplitude, we would have undesired large the frequency shift or phase shift. In the external modulation, we use the external modulator here, and laser would generate stable sinusoidal wave. But we need, of course, the external modulator. The setup will be more complicated if we compare with the direct modulation. But we can achieve high-speed modulation. The response of the modulator is much faster than the response of the laser itself. And we can achieve low chirp and precise modulation. As I mentioned, in the direct modulation, we control the optical output intensity directly by an electric current, injected electric current. This shows the relationship between the optical power and injection current. Here's a simple the model, but actual the response will be like this. We call this point the threshold current, and we defined some the DC bias voltage here to achieve the linear modulation, and we add some modulation signal, high frequency modulation signal with the bias current. We can get optical output like this. This is a basic configuration of direct modulation. If we change the bias point, for example, like this, the output power will be small, and we will lose the linearity. So we have to define the bias point properly. Okay, here I'd like to explain on the limitation of direct modulation. As I mentioned, in the direct modulation, the modulation speed is limited by the response of the laser itself. This shows the typical the laser frequency response. If we change the modulation frequency, the optical output power of the modulated signal would be like this. It has some peak, and the frequency will be described by this simple equation. Here is the threshold current if we can increase the current, we can increase the modulation, the highest modulation frequency. But of course, there is some limitation. We cannot put the large current in the laser diode. There is a damage threshold, so we have to properly set up the current J. And if we put the high frequency signal, whose frequency is higher than the frequency FR, the response will be very small. So we have to use the direct modulation in this frequency range. And it has the undesired chirp. As I mentioned, chirp means parasitic frequency and phase excursion. This shows the basic concept of the chirp. This direction shows the intensity, and in the direct modulation, we try to change the intensity, but we would have undesired frequency change like this, frequency excursion on that direction as well. So it would cause the degradation of the transmission performance and the undesired spectral broadening as well. So we have to take care about the frequency response and the chirp effect in the direct modulation. Here I'd like to show you some more on the chirp. As I mentioned, if we have the chirp effect, we have some frequency excursion and desired frequency shift. And by using the concept of instantaneous phase, the frequency chirp also will be considered as an undesired phase shift. And this the graph shows intensity modulation without chirp. There is no frequency excursion. So for ideal modulation, we have to generate the intensity modulated signal like this. Okay, here I'd like to give you the basic concept of the external modulation. As I mentioned, we use the external modulator to control the light wave. There are two types of effect which can be used for external modulation. The first one is electron absorption effect. By applying the voltage on the special material, we can change the absorption coefficient, so we can get the intensity modulation. Another one is an electro-optic effect, EO effect. As I mentioned in the introduction part, we can change the refractive index of the material. So we can shift the phase of the optical signal. Okay, here I'd like to explain the basic concept of EA effect a little bit. Horizontal axis show the wavelengths of the optical signal, and vertical axis show the absorbance. And here is a bandage of the semiconductor material. As you know, the photon energy is, if the photon energy is larger than the band gap energy, it will be absorbed. So if the wavelength is shorter than the bandage, the photon will be absorbed. But in a material which has EA effect, in the material which has an EA effect, if we apply the voltage, bandage will be shifted effectively. So if we put an optical signal along here, wavelengths along here, we can change the amplitude of output because absorptance depends on the applied voltage. This is the principle of EA modulator. The EA effect offers very fast optical modulation, and we can make a very compact optical modulators. So they are commonly used for the compact the transmission devices. But here, as I mentioned, we can control absorptance. But in addition to this, the refractive index also will be changed. So in the EA effect, the chirp effect is much smaller than in the direct modulation, but still it induces the chirp effect. This is an issue in the EA effect-based modulator, but it's very useful technology. Okay, here I'd like to explain the EO effect, electro-optic effect. In the EO effect, we can change the reflective index of the material. Some particular materials would have large EO effect along the particular crystal structure direction. We call it the C-axis. The lithium niobate, in short LN, is commonly used for EO effect-based modulators because it has large EO effect. The EO effect would be described by this simple equation. The change of the refractive index would be described by this equation. The Ni denotes the refractive index along X direction, Y direction, or Z direction. In the lithium niobate modulators, the Z-axis would be set to the C-axis. So C-axis along to the Z direction. And EJ this denotes the applied electric field. So R33 denotes the refractive index change on that direction induced by the electric field on that direction. Actually, in the lithium niobate, the EO effect will be the largest in R33. That means the EO effect on C-axis induced by the electric field on C-axis. So we have to align the applied electric field as shown here, and the electric field of light wave also on that direction. By using this configuration, we can get large EO effect. There are various types of material which can offer large EO effect. For example, lithium tantalate or indium phosphide. But the lithium niobate is commonly used because of the well-matured, established the fabrication process and the stability of the device and so on. Okay, I would like to move on to the next topics. Phase modulator based on electro-optic effect. As I mentioned, by using the electro-optic material, we can control the refractive index. In other words, we can change the optical phase. So by using the simple configuration, we can configure the optical phase modulator. Here's an example of optical phase modulator structure. We feed the optical input signal from here, denoted by Ft, and here's an optical input, and output will be described by this simple equation. We can get the phase shift proportional to the input signal. And here's a coefficient which bridges between the actual voltage of the electric input and the induced optical phase. We define this one half-wave voltage. If we apply the electric signal whose voltage is equal to half-wave voltage, for example, you can see if we put it here, the phase shift should be equal to pi. So V pi means required electric signal voltage to induce 180 degrees phase shift. Here is the response of the phase modulator. If we put the modulating signal up to half-wave voltage V pi, we can get pi phase shift. So in that case, the amplitude of the modulating signal should be equal to V pi. And if we measure the amplitude by the peak to peak, the voltage should be equal to V pi, as you can see here. This is some basic function of the phase modulator. Here I'd like to talk about the response limitation due to electrode length. As I mentioned, lithium niobate has large the EO effect, but we need a few centimeter long devices for conventional titanium diffuse waveguide devices. If we compare the EO effect with other devices, the lithium niobate has a large EO effect, but it's not large enough to make a small device. This is an issue of the EO modulator. So electrodes should be designed by transmission line theory. Otherwise, the response is limited by the capacitance of the electrode. So we need to carefully design the transmission line structure to achieve the high-speed response. Here's an example of the electrode structure. Coplanar waveguide, it has two ground electrodes and signal electrodes here. By using a transmission line theory, we can control the characteristics impedance and the velocity of the signal on the electrode. And we have to place the optical waveguide where the intensity of electric field is strong enough, as you can see here. To achieve the high-speed ablation, here's another issue, velocity matching for effective modulation. As I mentioned, we can control the speed of the signal on the electrode by designing the electrode structure. If there is some big difference in the velocities of the electric signal and the optical signal, modulation efficiency would be degraded because the propagation delay will be large. Propagation delay along the modulator will be described by this equation. Here is the difference of the effective refractive indices for electric signal and the optical signal. In other words, the speed of the electric signal and the light wave signal. And the expected bandwidth of the modulation device can be described by this equation. Of course, if we can increase the length of the device, required voltage will be small. But if there is some residual velocity difference, we would have a trade-off relationship between the length and the modulation bandwidth. This is one of the issue in the designing the EO modulators. Okay, here I'd like to move on to the fourth of the topics, Waseda modulator based on phase modulation. Firstly, I'd like to explain the Waseda interferometer. It's invented by the Mach and Sender in 1891. It has two optical paths like this. There are two half mirrors. The optical wave would be divided into two and combined together again. And if we change the phase difference between these two optical signals, we can change the intensity of the signal here. So the output optical power depends on the phase difference between two paths. If the phase difference is equal to 0, we can get the constructive interference. That means that we can have the maximum output power. If the phase difference is equal to 180 degrees, due to the destructive interference, the optical power goes to minimum. In the ideal situation, it should be close to 0. This is the basic the configuration of Waseda interferometer. Okay, here I'd like to talk about the half mirrors on the integrated circuits. In the Waseda interferometers, half mirror would play important roles. So we should consider how we can configure half mirrors on the integrated circuit to make the Waseda modulators. We use Y-shaped junction, we call it Y junction, to form the half mirrors. Here is an optical input, and in the Y junction, we can get a two optical output. We can divide it into two, as you can see here. But if we look at the mathematical structure of this device, it has another input coupling to radiative mode. In half mirror, we use only one input port here, and we can get two optical signals. But here is another unused input port. To understand the mathematical structure of the half mirror, always we have to take care of this part as well. So in Y junction, there are two input ports, but we don't use this one. We use only this one, and we can get the two optical output. Here's another half mirror. We use two input ports, but we don't use one of output port. it's associated to coupling to a radiative mode. We use only optical output on the guided mode. So we use a pair of Y junction, and we can form the mass center interferometer on the integrated circuit. It seems to be a one input and two input device, but virtually here's another input, and it looks like a two input and one output device, but here's another virtual output port. So to describe these structures mathematically, we should take into account this part. But in an actual device, we don't use the coupling to the radiative modes. This is a very important feature to understand the function of the function and the physics of the mass center modulators. Okay, here I'd like to talk about the amplitude of the light waves at the Y junctions. Here's an optical input. The input is the light wave is divided into two. So the amplitude here will be described by this equation, 1 over square root 2 here. But if we put the light wave here, the output signal would be described by this, because the 50% of the optical power would be radiated to the radiative mode if we put the optical signal only here. This is some very important point to understand the Y junction. But if we put another optical signal here, and if we can get the constructive interference here, we get the destructive interference on the radiative mode. So we can get the maximized output. But if we look at the each element, just by passing the half mirror part, the power would be half. That means the amplitude would be divided by square root 2. This is a very important feature of the Y junctions. Okay, here I'd like to explain the basic structure of mass center modulator. It has mass center interferometer consisting of two Y junctions. And here is an optical phase modulator to control the phase difference on the optical waves in the two optical paths. So we can control the optical output. This is the basic configuration of mass center modulators. This shows the basic principle of mass center modulator. As I mentioned, by changing the phase difference, we can control the optical output power. In the on state, the phase difference would be 0 degree, and we can have the constructive interference on the waveguide mode, and we can get the maximized output. In the off state, the phase difference would be 180 degrees, and we would have the destructive interference on the waveguide mode and constructive interference on the radiative mode. So we can have the minimum output on the waveguide. This is a basic principle of the mass center modulator. Once again, in the off state, we would have the destructive interference on the output port, but constructive interference on the radiative mode. Here, I'd like to give you a simple mathematical expression on mass center modulator, MZM. This is a basic structure of MZM. It has two phase modulators. GT over 2 denotes the induced optical phase shift by the optical phase modulator 1. And here's another optical phase modulator, the phase shift is minus GT over 2. So we have the same amplitude phase shift, but the polarity is different, plus phase shift and the minus phase shift. And optical signal on the upper arm can be described by this equation. Optical phase shift is GT over 2. Here is another optical signal. Phase shift is minus GT over 2. So this plot can be described by a cosine function. So by changing GT, we can control the amplitude of the optical signal. In other words, optical intensity can be controlled. And if the GT is equal to a multiple integer of 2 pi, we can get an on state. The intensity would be maximum. This component is equal to 1. In the off state, this component goes to 0. So we can get intensity control like this. And halfway voltage for Waseda modulator will be defined by this here. From here to here, we need the V pi, the voltage, halfway voltage, to switch the optical modulator from on state to off state. If we apply the halfway voltage on Waseda modulator, we can get the 180 degrees phase difference between these two arms. But we have to take care on this issue. Even we apply the halfway voltage on the Waseda modulator, the induced phase on the optical phase modulator in each arm will be just 90 degrees. Here plus 90 degrees. Here minus 90 degrees. In total, we get 180 degrees phase difference. So there is some difference in the definition of the halfway voltage in the Waseda modulator and the phase modulator. Here I would like to explain more on the Waseda modulator. As I mentioned, in the optical phase modulator, we can control the optical phase if we change the modulating signal voltage like this. For example, in the modulator 1, the optical phase should be proportional to the applied voltage. And here the optical phase in the modulator 2. We induce minus optical phase. So here we get the pi phase difference. But as I mentioned, the V pi for the phase modulator is far from here, around here, around here. At this point, we get just a pi over 2 phase shift at the each phase modulator, and in total we get a pi phase difference. And if we look at the optical amplitude, here we get +1, and here, if the phase difference is equal to pi, the optical amplitude is 0. And here's another on state, but here the amplitude is equal to -1. So these 2 points corresponding to the on state, but there are 2 types of on state. If we look at just the intensity, the intensity is maximum here and here. But if we look at the amplitude, +1 and -1, it's also a very important feature of the Waseda modulator. So please be careful. If we use the amplitude, we have to select the bias point or the modulation condition properly. Basically, Waseda modulator can be used as an intensity modulation device or amplitude modulation device, but it can be used for binary phase shift keying. In a binary phase shift keying, we use 0 degree and 180 degrees. We call it phase shift keying, but in other words, we call it amplitude shift keying with two symbols, +1 and -1. +1 and -1 can be described by the 0 degree and 180 degrees. It's a special case of the phase shift keying. So that's why we can generate binary phase shift keying signal by Waseda modulator. Waseda modulator is an amplitude modulation device. As I mentioned, we have 2 points on state with +1 and -1. By using these 2 points, we can get the 0 degree and 180 degrees, the +1 or -1. If the G equals 0, we can get 0 degree symbol. If the GT is equal to 2 pi, we can generate -180 degrees. To get these two states, we have to apply the halfway voltage of Waseda modulator, but it corresponds to the halfway voltage of the phase modulator embedded in the Waseda modulator. This is also a very important point. Okay, here I'd like to talk about the device structure for push-pull ablation. As I mentioned in the Waseda modulator, we use the 2 phase modulators. For ideal amplitude modulation, we have to have the phase modulation like this. Here, G/2 minus G/2. The amplitude of phase shift is same, but here is a plus phase shift, here is a minus phase shift. We call it push-pull ablation. If we can have ideal push-pull ablation, we can get the ideal amplitude modulation. To achieve the push-pull ablation, we use the X-cut lithium niobate. In the X-cut lithium niobate, the C-axis along X direction. In the modulator, we define Z direction here, the Y direction along the waveguide, and X direction like this. We call it X-cut Waseda modulator, X-cut lithium niobate wafer Waseda modulator. By using this, we can get the plus phase shift here because the electric field along the C-axis. And here, the electric field along the Z-axis, but direction is flipped. So we can get the minus phase shift. So we can get the push-pull ablation. Okay, here I'd like to talk about another structure, Z-cut lithium niobate wafer. The C-axis is along the Z direction, like this. And optical waveguide can be placed here and here. In that case, we can get the strong electric field here. And we should put another waveguide along here to get the large in the phase. So we utilize this point and this point. So we can get a large electro optic effect. But the intensity of the electric field is not equal here and here. So the push-pull operation would be asymmetric. This is an issue. As I mentioned, by using X-cut wafer, we can get the ideal symmetric push-pull operation. Here is the field distribution. By using these 2 points, point B and point E, we can get the large interaction between the modulating signal and the optical signal, and we can get a almost ideal push-pull operation. But electric field is weaker than in Z-cut. This is an issue. So if we want to get the symmetric push-pull operation, normally we have to use the X-cut. If we want to increase the modulation efficiency, we can use a Z-cut wafer. Okay, here we talk about the asymmetric push-pull operation. In this case, the modulation efficiency has difference in the modulator 1 and 2. As I mentioned, if we use a Z-cut structure, the modulation efficiency would have some asymmetry. In this case, the modulator 1 efficiency modulator 1 is larger than in modulator 2. If the phase difference is equal to pi, we can get the zero off state and on state here, and here is another on state. But here's the phase shift difference, so we would have the phase shift in an optical output. So that means the modulator would have chirp effect. This is an issue in some particular application. As I mentioned, if we use a Z-cut lithium niobate, we can increase the modulation efficiency. But for symmetric modulation, push-pull operation, we have to use an X-cut lithium niobate. There is a kind of a trade-off relationship. To mitigate this trade-off relationship, advanced device structures proposed. Here's one of them. They use a domain flipping technology. As I mentioned, there is a special direction of the crystal. For example, here the Z-cut, we use a Z-cut lithium niobate, and the C-axis along the Z direction. But we can flip the direction of the C-axis to the minus Z direction, for example here. So we can flip the polarity of the EO effect, this one, this part and this part. And here we use a conventional Z-cut lithium niobate modulator structure. Of course, there is some asymmetry. And here is the C-axis flipped region. If we use a normal electrode, of course, the modulation would be minus. So here is a plus in this phase, here's minus in this phase. So finally, the modulation efficiency goes to 0. But if we flip the location, if we shift the location of the electrode, I mean flip the ground electrode and the hot electrode, we can keep the modulation polarity. I mean here C direction is plus, and here the plus electrode, minus electrode, and here C direction minus, and electrode is also flipped, the ground and the signal. So in -1, would be squared. I mean, -1 plus -1 equal +1. So we can keep the modulation efficiency, and we can increase this symmetry in the modulation scheme. So we can achieve almost symmetric push-pull operation even in the Z-cut lithium niobate modulator. If we want to understand some more detail, you can check the reference, and also you can read my book as well. Here is another device structure. They also use the domain flipping technology. They divide the modulating signal. So the electric field has the symmetry, and the direction of the electric field is same. So if we use just a simple Z-cut device, we get the plus phase shift and the plus phase shift. That means there is no interference. But in that case, the upper part is domain flipped. So we can get, for example, minus the optical phase shift here and the plus phase shift here. So we can get symmetric with the push-pull operation. Here's another option. If you're interested in the detail, you can check the journal paper here. Okay, I'd like to move on to the last part of the video, precise optical modulation, which includes the vector modulation and the high extinction ratio modulation. Okay, here I'd like to explain the basic concept of vector modulation. As you may know, the signal can be described on the complex number plane, two-dimensional plane. Real part and the imaginary part. Real part correspond to the cosine part. Imaginary part correspond to the sine part. As I mentioned before, the modulation can be described by the amplitude modulation or angle modulation. Angle modulation can be mathematically expressed by the modulation on the instantaneous phase, and this part corresponds to the amplitude modulation part. By combining them, we can control the optical signal on the complex plane. As you may know, we can call it the vector modulation. Here, I'd like to show you the vector modulation using the dual parallel Mach-Zehnder modulator. It has two small Mach-Zehnder modulators embedded on a large Mach-Zehnder structure like this. As I mentioned, the vector modulation can be achieved by the amplitude modulation on cosine component and the sine component. By using the optical phase shifter, we can define cosine component and the sine component. And on the cosine component, we can change the amplitude by this Mach-Zehnder modulator 1, and here is Mach-Zehnder modulator 2 for cosine component. And here's a mathematical expression for the vector modulation by using dual parallel Mach-Zehnder modulator. Here is a cosine component. The amplitude of the cosine component will be described by cosine factor, which is given in the part of the basic principle of Mach-Zehnder modulator. And this part shows the sine component. I means the 90 degrees phase shift, so this component corresponds to the imaginary part. And the imaginary part of intensity also can be controlled by this factor. So we can achieve the two-dimensional the modulation. We call it vector modulation. By using the vector modulation, we can generate various types of signal. This is an example, QPSK, quadrilateral phase shift keying. It has 4 symbols, as you can see here. We can generate the quadrilateral phase shift keying signal by using 4 pairs of the electric signal, as you can see here. If we put 0 to these 2 Waseda modulators, we can get this component, because cosine component is 1 and the sine component is equal to 1. And by changing the phase shift in Waseda modulator 1 and 2, we can select the symbols from 4. This is the basic configuration of the quadrilateral phase shift keying, and it's commonly used for large capacity transmission systems. By using the combination of the Waseda modulators, we can generate more complex signals. You can see here, and this is symbol diagrams of the QPSK, and in this configuration it has 16 symbols. Of course, we can generate more complex modulation format. If you want to learn more, you can check the references listed here. As I mentioned, the spectrum of optical phase modulated signal should be described by the Bezel function. This is the simplest example. Just the output of the simple optical phase modulator would be described by a series of the Bezel functions. The intensity and amplitude of the carrier component should be equal to 0th order Bezel function, and here the first order sideband, the first order Bezel function. Amplitude is equal to first order Bezel function. Here the second order sideband, amplitude would be proportional to the second order Bezel function. And in the lower sideband, the sum component, the polarity will be flipped. If you're interested in the detail, please check the equations in this book. Due to the limitation of the time in this video, I will skip the detail on the mathematical expression. Okay, now this shows an example of sidebands in Waseda modulator described by the Bezel functions. As I mentioned, the optical phase modulator would generate many sidebands, as you can see here. Here's another phase modulator, but here phase shift is plus and phase shift minus, so there is some difference in the sideband component. And also we should control the optical phase shift by bias. We can control the phase relationship of the sideband, and we can calculate the expected output spectrum by using such a mathematical formula. Of course, I don't have enough time to explain the details. If you're interested in, please check the reference. Okay, here I'd like to move on to the last topics in this video: high extinction ratio Waseda modulator. As I mentioned, in the ideal Waseda modulator, in the off state, the output goes to 0. But of course, in the actual devices, there are some imbalance due to fabrication error or something else. So even in the off state, we would have some residual output. Typical output would be minus 20 dB or minus 30 dB with respect to the on state. We call it extinction ratio. For conventional transmission system, the extinction ratio higher than 20 is good enough. But for some particular application in measurement or something, we need to increase the preciseness of the modulation. Here's an example of the device structure to increase the extinction ratio. The idea is very simple. Just by using an intensity trimmer, we can compensate the fabrication error. By using small mass center modulators, we can compensate imbalance in the large mass center modulator. By using such configuration, we can achieve the extinction ratio higher than 70 dB. Extinction ratio is associated to the intensity of residual component, but it has an impact on chirp or some other modulation the characteristics. Okay, here I'd like to talk about the optical phase error due to the finite extinction ratio. If the extinction ratio is almost infinity, in that case 60 dB, the optical output would on the real part +1 to -1, no phase difference. This graph shows the optical output on the complex plane. So this direction corresponds to the 90 degrees phase difference component, imaginary component. In a perfect the mass center modulator, output would always be on the real component. If the extinction ratio is equal to 60 dB, it's on the real axis, x-axis. But if the extinction ratio is 15 dB, it has some chirp effect. I mean, it has some imaginary component. And the separation corresponds to the inverse of the extinction ratio. Here is some simple expression, relationship on the extinction ratio and the optical output. And here is some graphs, the phase error versus the amplitude. If the extinction ratio is 60 dB, the phase error is almost 0. On the origin of the complex plane, this is a special point. Always phase error will be minus 90, but the intensity of the optical power is very small, so this part will be negligible. But if the extinction ratio is 20 dB, it has non-negligible phase error. If we purchase the conventional modulator, the performance will be around here, 20 to 25. So if we want to use the modulator in some particular purpose related to the fine measurement, we have to take into account this effect. This shows the typical response of the optical phase and the power with the finite extinction ratio. We change the voltage from here to here, so the phase will be plus 180. That means -1 on the real axis. And in the ideal modulator, it should be on -1, and suddenly it jumped to the 0, but it never happens. It has some, it should be described on the continuous curve, and this point corresponds to null phase error due to the finite extinction ratio. And even in the off state, as I mentioned, it has some the finite output. If we use the modulator close to off state, we would have large impact of such error. But if we use the close to off state, we can reduce the required voltage because we can easily change the phase or amplitude. If the extinction ratio is very high, even if the modulation signal amplitude is very small, we can transmit the signal. We have demonstrated such function. Here's an experimental setup to show the importance of the extinction ratio. The modulation signal amplitude is just 2% of the V pi. So we can largely reduce the required electric signal power. But if the modulation depth is very small, we would have large impact on the finite extinction ratio. If the extinction ratio is 21 dB, we would have large unmodulated component. But if the extinction ratio is 54, even if the modulation depth modulation signal is very small, we can get the modulated signal, ideal modulated signal. Here's a setup. Here's the Paris pattern generator, and we use a filter to get the dual binary signals. If you're interested in detail, please check this the journal paper, and we measure the waveform by using the oscilloscope and the error detector. Here is the relationship between the extinction ratio and the sideband optical power. Sideband optical power carries the information. If the modulation depth is very small, we would have the large impact on the extinction ratio. But if the extinction ratio is higher than 40, even if the modulation signal is very small, we can have enough sideband power. Here's an eye diagram. Eye diagram shows the quality of the signal. Even if the modulation depth is very small, the 2% modulation, we can get a very nice waveform. If we increase the modulation depth, even if the extinction ratio is 26 dB, we can send the information. But if the modulation depth is 2%, if the extinction ratio is 26, there is no signal detected. So by increasing the extinction ratio, we can effectively increase the modulation efficiency. This is an important feature of the precise optical modulation. Okay, this is my last slide. I talked about the role of optical modulation in photonic networks. And I talk about the basic concept of direct and external modulation. And in this presentation, I focus on EO effect, electro-optic effect modulators, because they can offer high-speed modulation and precise modulation. EO effect induces the optical phase shift. So we have to understand optical phase modulation first to discuss the Waseda modulator or other complicated modulators. In the fourth part of this presentation, I talked about the Waseda modulator. I offered simple mathematics, and I had a discussion on the trade-off relationship between the Z-cut lithium niobate and X-cut lithium niobate. Z-cut lithium niobate wafers can offer effective modulation, but we would have undesired asymmetric push-pull operation. To solve these issues, various types of advanced device structures are proposed. I showed just some examples to you in this presentation. In the last part of this presentation, I talked about vector modulation. The vector modulation plays very, very important roles in high-speed transmission systems. The QPSK is commonly used for long-haul transmission. And in the last part of my talk, I explained the importance of the high extinction ratio modulation. The extinction ratio shows the preciseness of the optical modulation. If we can increase the extinction ratio, we can enhance the modulation efficiency effectively. Even with the small amplitude, the electric signal, we can generate the high quality optical signal if the extinction ratio is high enough. And I listed two references, as I mentioned before. The first one is on electro-optic modulation for photonic networks. If you're interested in the EO modulation, I think you can find more detailed information in this book. And another one is on wired and wireless seamless access system for public infrastructure. In sections 5.3 and 10.3, you can find useful information to understand the EO modulation more. Okay, I hope you enjoyed my talk and you could learn something on EO modulation technology. Please enjoy and play with the EO modulators. Thank you very much for your attention. Goodbye.